Hello everyone, today I want to introduce my project which is called OFDM Channel Estimation and Sequence Recovery using Deep Learning. So the task in this project is channel estimation, which is to estimate the channel state information, and sequence recovery, which is recovering this transmitted sequence from the received sequence. So the two tasks are performed in the orthogonal frequency division multiplexing system, which is called OFDM. So OFDM system has the following features. The first one is that it divides the data streams into many substreams. So in the traditional community system, it just uses the entire bandwidth to transmit one bit. So in this way, this entire bandwidth is one thing. So when there is some interference, this bandwidth can easily be affected. But if we have so many substreams, the interference can only affect a very few number of substreams. Also, these substreams are carried by many subcarriers, and in OFDM system, each carrier is orthogonal to other carriers. So in this way, because there cannot be any interference between those orthogonal carriers, so we can eliminate the interference in this way. So the neural network that we use in this project is artificial neural network, which is ANN here. It is the simplest kind of neural network. It only has fully connected layers, and the input and output of this network are only vectors. So the ANN that we use has one input layer, one output layer, and 3 hidden layers. So those 3 hidden layers has 500, 250, and 120 nodes respectively. So now I will introduce the system architecture of this project. So firstly, we want to combine the original data sequence to be transmitted with the channel model and put them into the simulation program. And this simulation program can generate the simulated received data sequence. And this sequence is put into the neural network as an input. And this network can output the predicted transmitted data sequence, which is SK here. And this XK is compared with the original transmitted data sequence, which is XK hat here. And then we can calculate the loss and backpropagate our neural network. So now I will introduce the simulation method of this project. The raw data that we have for the simulation are many pilot files, and each pilot file contains many sequences of pilots. So the first step of the simulation is that we want to check whether the number of bits that we want to transmit, which is K here, is smaller than the number of pilots, which is P here. If so, all the carriers in this transmission are pilot carriers. But if K is bigger or equal than P, we can assign a pilot carrier for every K divided by P data carriers. And then we want to do the data modulation. So in this step, we just randomly generate a bit sequence as the data sequence that we want to transmit. And we can form complex numbers from this sequence. So the way to do that is we align every 2 adjacent bits in this sequence to form a pair. And we use one bit in this pair as the real part, and the other one bit as the imaginary part. And in this way, we can form a complex number. And the complex numbers that we get are put into the data carriers. So finally, we want to fit our transmitted sequence into the channel conditions. We just use IDFT to transform these sequences from the time domain into the frequency domain, and then we convolve the sequences with the channel conditions, which are pilot sequences, and we add noise to the result. So the evaluation method in this project is that we plot bit error rate, which is BER, versus the signal to noise ratio, which is SNR, and we get a curve. So BER equals the number of bit errors divided by the number of bits that we received, and SNR equals the power of the signal that we transmit divided by the power of the background noise. So we can expect that a good communication system should have low BER and high SNR. And we can also expect that BER should decrease when SNR increases, because when the power of the transmit signal is very big, you can hear the signal clearly, and your bit error rate cannot be high. So in training and testing, we partition the 400 pilot files that we have into 300 training files and 100 testing files. And there's no validation needed in this experiment because we just directly use the hyperparameters in the original paper. And we generate 1000 bit sequences to be transmitted for each pilot sequence, so that we have 1000 pieces of training or testing data for each channel condition. So in this project, we want to explore different simulation methods, and we want to see whether the change of a simulation method can affect our sequence recovery performance. So the first thing that we want to explore is the number of pilots. So pilots are sequences loaded by the receiver, and they can be used to estimate the channel state information. The way to do that is that the transmitter transmits these pilot sequences to the receiver before transmitting real data. And when the receiver gets the received pilot sequence, it compares these sequences with the ground truth pilot sequences. And in this way, it can estimate the channel state information. So selecting the right number of pilots is actually very tricky. So we want to test the optimal number of pilots in this experiment. And this is our experiment result. We can see that when we use 64 pilots, we can achieve a lower BER than using 8 pilots. The reason is that when we use more pilots, we can have more information about the channel state information, so that we can recover our transmitted signal more accurately. The next thing that we want to explore is cyclic prefix, which is called CP. So CP is actually a kind of guard band. So in OFDM system, when we calculate a bit in a symbol, we use the last L transmitted bits. So when these symbols are adjacent to each other in the transmission, when we calculate one bit in this symbol, we may use the bits in the last symbol to calculate. So this causes some interference. So we want to separate those symbols so that when we calculate one bit in the symbol, we only use the bits in this symbol to calculate. So the way to separate them is using this guard band. So now we want to test the effect of adding CP, and this is the result. We can see that when we use CP, we can have a lower BER. And actually there are two kinds of CP. The first one is ordinary CP, which are just some subsequences of the sequence that we want to transmit. And the second one is noisy CP, and it is just some randomly generated sequence. And we compare the performance of using these two kinds of CP. We can see that the ordinary CP can have a lower BER. The reason is that it is a subsequence of the sequence transmitted, so it is meaningful when it is used to calculate the bits in this sequence. It is more accurate, but noisy CP cannot give any information. It is randomly generated. So the last thing that I want to explore is clipping. So OFDM has a large crest factor, which is the power of the peak bits divided by the power of the mean in this sequence. So if we have a large crest factor, that means the variance in this signal that we want to transmit is very large. So when these peak bits pass through the nonlinear devices, they can suffer big distortion, and distortion can cause a higher BER. And the way to eliminate this distortion is to eliminate these peak bits. So the way to do that is we check the value of every bit, and if it is within the threshold, we just keep it. But if it is higher than the threshold, we just reset it to the value of the threshold. So this is an experiment result of using clipping, and we can see that the BER is actually higher than the long clipping methods. The reason is that we may set the threshold too low, so that we not only clipped those peak bits, we also clipped some lower bits, which is unnecessary. So we can try higher threshold, and since threshold is controlled by this CR, we can use higher CR. And we can see that when we elevate the threshold, the performance of this clipping method is very close to the unclipping method. And when the CR equals to 2, we can even achieve lower BER than the long clipping method when the SNR equals to 25. And there are some related work about channel estimation. So traditionally we use some methods like least square, least mean square, minimum mean square error, or linear minimum mean square error. So I will not introduce these methods here in detail. So for the conclusion of this paper, I creatively use neural network to do channel estimation and sequence recovery. And I did many experiments about different simulation methods and tested many techniques that can be used in the simulation, which is not done by the original paper. And finally, I found that using 64 pilots with ordinary CP and the clipping of CR equals to 2 can give us the best performance. So this is my presentation. Thank you.